Hey guys, this is an introduction to organic chemistry, and it gives a really good foundation of concepts that will be learned in organic chemistry. So this is one of my favorite topics. If you get a really good foundation here, it will definitely help you for the future things to learn in this course. So, in essence, organic chemistry is the study of carbon-based compounds. And it surrounds us. All of the chemicals around us are typically organic based. And examples include clothes and foods and medicines and gasoline and refrigerants and soaps. And I can just keep reading the presentation, which you could do as well. But I will try to limit the amount that I just read the presentation because you can do that. I just want to focus on some fundamental concepts, again, that you should become really comfortable with. Organic compounds and products can be found in nature. They can also be synthetically produced. And here are two examples of organic compounds. Methane is natural gas. Organic compounds typically contain hydrocarbon backbones, and you can see that this structure here contains hydrogen. I just circled carbon. It contains hydrogen and carbon. Oxygen is also another common element in organic compounds. So the four most common elements in organic compounds include carbon, hydrogen, oxygen, and nitrogen. And then there are fewer, there's also phosphorus and iron and sodium and potassium, and a lot of electrolytes come into play when we start talking about body systems. So, ethanol is the alcoholic that can be found in alcoholic beverages, and one of the things that you're going to get really, I'm fumbling on my words, I'm sorry. One of the things you're going to get really good at is being able to look at the structure and see this OH group here. With this OH group here, and without any other additional groups attached, that will categorize this compound as an alcohol. Alcohols, when you name them, end in OL. This category of compound here is called an alkane. An alkane, and there will be a further discussion of this in the duration of this slideshow, but I'm just going to introduce things as I can and as I see fit. So an alkane is a carbon, it's a hydrocarbon that contains all single bonds. So meth, the prefix meth means one. So an alkane with one carbon is called methane. If we had an alkane with two carbons, and each of these carbons would be surrounded by hydrogens, you'll notice in this drawing I have all single bonds. The prefix for two is eth. So here you can see we have two carbons, which is why this is called ethanol. Alcohol names end in OL. The prefix eth means two. Since this is an alkane, the name of this would be ethane. Okay, so we've learned about two types of compounds so far. Alkanes, which are hydrocarbons containing all single bonds. Their names end in ane. And alcohols, which are hydrocarbons that contain an OH group attached. This is called a hydroxyl group, and the name of this is ethanol. So if you see here, capsaicin is the hot ingredient that causes the spiciness in peppers. There is a lot of structure here. So one thing that you have to become good at is recognizing different groups. So let's see if there are any alcohol groups in this molecule. And I do see one right here. So attached to this carbon, this hydrocarbon, is this OH group. That is considered an alcohol group. You will learn that this right here is called an aromatic group. This structure right here, in which we have carbon, oxygen, carbon, is called an ether. This structure right here, in which we have nitrogen, carbon, double bonded to an O, is called an amide. This portion of this molecule consists of a carbon chain with no double bonds. This portion would be an alkane. When you have a double bond in a carbon chain, so if we were to look at all of this, and you have a carbon chain in which there is at least one double bond, it's called an alkene. And if you notice the arrangement of the hydrogens across this double bond, we have one hydrogen here and one hydrogen there. That is called a trans geometric isomer. If we were to have a hydrocarbon chain that included this double bond in which, I don't know what's happening here, in which the hydrogens were on the same side, this would be called cis. Now, it is not incredibly important that you memorize all of this right now. I am strictly using this as an introduction, and each of these things will be taught as they come along in the duration of this course. Here is another common organic compound that you might be familiar with, caffeine. And we will learn that, again, this is an amide. We have an amide here, and here we have what's called an amine. And this is an amine. And again, you will become more familiar with that as we go through. All right. So when we represent organic compounds, in chemistry class, you probably learned how to draw Lewis structures. These two electrons are electrons that are being shared between each of these elements. And when we represent them in a drawing form, this is called a structural formula. So this line represents a covalent bond. Electrons are being shared between these two elements. So carbon will always form 4 covalent bonds. That is just the nature of the carbon element. Carbon has 4 valence electrons. So an element with 4 valence electrons, when you draw this dot structure, you will put each electron by itself before pairing up. And wherever you have an electron by itself in a dot structure for an element that is a potential bonding site. For example, nitrogen has 5 valence electrons. So if I draw the dot structure for nitrogen, I do not know what is happening with this thing. All right, 5 valence electrons. I have 1. I don't know what's going on. This is ridiculous. I'm angered. This is crazy. I'll draw it over here. Nitrogen has 5 valence electrons. 1. I don't know what's happening. This is driving me crazy. Here, I'll try it here. Nitrogen has 5 valence electrons. Oh my goodness. Maybe it doesn't want me drawing dots. It has a problem with dots. I can draw dots like this. This is crazy. 1, 2, 3, 4. Those dots are tiny. Those are tiny dots of electron structures. I guess we'll have to make do. So I've added 4, and then a 5th would be added here. Oh my goodness. It really just does not like me drawing circles. I'll draw big circles. I wonder if you can actually see this on the screen. I'm getting this weird pop-up. Alright, so if we look at this dot structure, we can see that nitrogen has 3 electrons by itself, so it commonly forms 3 covalent bonds. That will be discussed also further in this presentation. Hydrogen always forms 1 covalent bond, always. Alright, so here are some examples of where we have single and double and triple bonds. So between these 2 carbons right here, we have single bond. That single bond is represented by that single dash. Here we have 2 pairs of electrons being shared, so that is a double bond, and we draw double bonds like this. Here we have 3 pairs of electrons being shared, and we draw triple bonds like this. So one thing that you will notice is that in every single case, each carbon is surrounded by 8 total electrons, which, according to the octet rule, is what elements need to do to have their electron configuration stable. So this carbon has 2, 4, 6, 8 electrons. This carbon right here has 2, 4, 6, 8 electrons. This carbon right here, since these are being shared, has 2, 4, 6, 8 electrons. And when we talk about carbon always having 4 bonds, you can count the double bond as 2 bonds. So this carbon has 1, 2, 3, 4 bonds. This carbon right here has 1, 2, 3, 4 bonds. I hope that you can see the dot moving in this presentation as I am moving it around. So, and what you notice about hydrogen is that there is always only 1 dash associated with the hydrogen. So hydrogen is stable with just 2 electrons because, according to the octet rule, an atom will react to achieve a noble gas configuration. The element helium has 2 valence electrons. So helium, if this is its electron, outer electron shell, when hydrogen is sharing these 2 electrons right here, or these 2 electrons right here, it feels that it has its 2 electrons, so it becomes stable. So hydrogen is always involved with a single covalent bond. Sometimes with organic compounds we have chains of carbons, and sometimes we have rings. So the prefix prop is associated with 3. This is an alkane. It contains carbons. There's hydrogen and carbon, and there are all single bonds, so the name of this is propane. Since these are connected in a circle, this is also an alkane. It's called a cycloalkane. There are 3 carbons, again, associated with 3 is the prefix prop. That makes this cyclopropane. Look at each carbon. Each carbon is surrounded by 4 bonds. 1, 2, 1, 1, 2, 3, 4. So sometimes we'll have elements other than carbon and hydrogen. Any atom that's not carbon or hydrogen is called a heteroatom. Each heteroatom forms a characteristic number of bonds determined by its location on the periodic table. So the common atoms that we will see include nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So some of these atoms have lone pairs, and some of them will not. These are all examples that have lone pairs. Now let me show you what I mean by that. So nitrogen has 5 valence electrons. When we draw that electron structure, any spot where there is a bond, an electron all by itself, is a potential bonding site. So nitrogen will often form 3 bonds. This right here is called a lone pair of electrons. So nitrogen commonly has 2 lone pairs. I'm sorry, I made a mistake. Nitrogen has 1 lone pair and it will form 3 bonds. Oxygen has 2 lone pairs. And it will often form 2 bonds. Fluorine has fluorine, chlorine, and bromine and iodine all have 3 lone pairs. So I'll draw this here. Fluorine has 7 valence electrons, so it will often bond to one thing. It will have 3 lone pairs. Either way, each of these elements now has 8 electrons around it. Okay, so here's a summary of that. Hydrogen will be involved with 1 bond. Carbon, which has no lone pairs, it has 1 electron by itself, will be involved with 4 bonds. Nitrogen will be involved with 3 bonds. Oxygen will be involved with 2 bonds. And any of the halogens, which include fluorine, chlorine, bromine, or iodine, will be involved with 1 bond. So a common double bond between carbon and another atom is this carbon-oxygen bond. This right here is referred to as a carbonyl group. Carbonyl group. If we look at this, we don't have a double bond in this one. Oxygen has 2 single bonds, and it's 2 lone pairs of electrons. Here, oxygen is involved with a double bond and still has its 2 lone pairs of electrons. So this is a common double bonded atom that we see in hydrocarbon chains. Now, when we talk about the structure of, I'm sorry, I have an itchy eye. I could stop the video, or I can edit this out, but I probably won't because I don't have time for that. Alright, so VSEPR theory stands for valence shell electron pair repulsion. I will never ask you to tell me what VSEPR stands for, but the central idea with VSEPR theory is that atoms are most stable when their electrons are as far away from each other as they possibly can. So if you have an atom that is attached to two groups, two atoms like this, it is going to have a bond angle of 180 degrees because these want to get as far away from each other as they can. If this is here, that's too close. So if it's going to get as far away from each other as it can, they're going to be in opposite directions. So let me just delete that. So when you have two atoms stuck to one another, the bond angle between them is 180 degrees. So when we're looking specifically at this carbon, this is one thing attached, this is a second thing attached to this carbon. The bond angle between these two is 180. Now I can then look at this side as well. If I look at this carbon, the first thing that's attached is this, the second is this. This bond angle is 180 degrees. That is called a linear orientation, or a linear geometric structure. If you have an atom surrounded by three groups, so let's say this is just an atom all by itself and it's attached to three things, in order for them to get as far away as they possibly can from each other, they're going to be spread out like this. This is called trigonal planar. If you could imagine this structure in which all of these are sitting flat on a table or up against the whiteboard, they would all be sitting flat in the same plane, and this bond angle between these three atoms here is 120 degrees. Now this structure here has a double bond, and when you look at it, this atom has three groups attached. So this is one group, this is one group, and this is one group. So when I'm looking at this atom right here, this bond angle is 120 degrees. And I can look at it with respect to this atom as well, and it acts the same. That is called a trigonal planar. When an atom is surrounded by four groups, it's called a tetrahedron. So if you could visualize this, this is my central group, and imagine this as like a tripod. I am not the best drawer. And then sticking up out of the tripod is that fourth thing. So this is called a tetrahedron, and the bond angle between atoms in a tetrahedron is very specific. It's 109.5 degrees. So when we are illustrating three dimensions on a page, sometimes you will see these features right here. So any bonds that are within the plane of the central atom are just drawn with a single dash. If there's an indication that a bond is sticking out in space at you, so sticking out in space at you, it'll have this wedge. And if there's an indication that the bond is going towards the back, away from you, you see this little dash, 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 dash. That means the bond is sticking behind. So if you try to imagine this in three dimensions, these would be in the same plane as each other. This one is sticking out at us, and this is going back into space. So this is one way that molecules can be represented in three dimensions on a page. Every single carbon that has four single bonds to it is a tetrahedral arrangement, and the bond angle will always be 109.5 degrees. Nitrogen is attached to three atoms with one lone pair. Now if we look at the simplest molecule of nitrogen, it is ammonia. Ammonia has its NH3, it has three hydrogens. and a lone pair of electrons up here. When you have a structure like this, the shape of this is called trigonal pyramidal. And if we had, so there are 4 groups around the nitrogen, right? There's this unshared, it's not an atom, but it's a pair of electrons. There are 4 things surrounding the nitrogen. 3 of them are atoms. When we had 4 things surrounding the carbon, our bond angle was 109.5 degrees. That is when we had 4 atoms surrounding the carbon. Here we have 3 atoms and 1 lone pair. Now let me tell you something about this lone pair of electrons. This lone pair of electrons is billowy. It's taking up a lot of space. See that? Billow, billow. Now, what tends to happen is it exerts a downward force on the rest of the molecule. So had this been an atom that was attached, our bond angle with 4 things being attached would be 109.5. Since this is not an atom and it's a lone pair of electrons, and it is pushing this downward force, it is putting this downward pressure, it's causing those hydrogens to come a little closer to each other than they ordinarily would. So this structure, if it was a tetrahedron, like this, the bond angle would be 109.5, but it's not. There is a billowy set of electrons there that is putting that downward force, so this bond angle is less than 109.5 degrees. I am not positive of the actual bond angle, but it doesn't even really matter. I am not sure what this 112 is here. That's really kind of bizarre. But what we see here is this, it's called trigonal pyramidal. I think that when you have a big thing like this being attached, it messes up with bond angles, and I'm not going to make you responsible for a lot of that. But trying to visualize, when we have a nitrogen in a compound, it's typically attached to 3 things, and it has this sort of tripod sort of arrangement. Now, when we have 4 things attached and 2 of them are lone pairs, we have an angle of less than 109. If we look at water, all right, again, if we had 4 atoms attached, the bond angle would be 109.5. When we had 3 atoms attached and 1 lone pair, the atom was a little less than 109.5. Now again, that is not assuming that we have like these more complex structures. When we have, let me just review, this shape is called tetrahedral. This was called trigonal pyramidal. When we have 3 things, two atoms attached and 2 sets of lone pairs, this angle is less than 109 degrees. Now, what is it specifically? It's just really going to depend on less than 109.5. Sorry, it's going to depend on what the elements are. The major takeaway here is that when you have an oxygen in a structure, you end up having this bent region. So this is a summary. 2 things attached. We have a 180-degree angle. 3 things attached with no lone pairs. We have a 120-degree angle. It's called trigonal planar. When we have 4 atoms attached, it's called tetrahedral, and it is a bond angle of 109.5. When we have 3 atoms attached and 1 set of lone pairs, it says about 109.5. I'm telling you it's a little bit less because there's this downward force. And when you have 2 atoms attached and 2 lone pairs, they say about 109.5. I'm saying even less than 109.5 because this structure just gets cinched down. It gets pushed down. They get pushed closer together. So if we are representing molecules in organic chemistry, we have different ways of representing them. This is a full structure. That's a lot to write. So a condensed structure, all of the atoms are drawn in, but we generally do not include the lines. Now, sometimes you will see condensed structures like this, CH3, and then a line there, CH2, CH2, CH3. Sometimes you will see them all in a line like this without any of the lines. Okay. Now if you look at this, there are 4 carbons, 1, 2, 3, 4. 1, 2, 3, 4. And at the end we always have a CH3 because the end carbon is always going to be attached to 4 things. If one of them's carbon, the other 3 have to be hydrogen. Your middle carbons are always attached to 2 hydrogens. And here this end carbon is also attached to 3. So that is in a structure like this. This is an alkane. It's a hydrocarbon chain with all single bonds. The name of this is butane. And the prefix but means 4. If you have a branched structure like this, you will see a line there. So this is showing that this CH3 group is attached to this carbon. You might see it like this. You may also see this written down like this, and it is exactly the same thing. Now what you do notice is that instead of this saying CH2 like it did, it now says CH. Sometimes you can really shorten things up. This is really not that big of a shortening up of things, but if you have this repeating CH2 in a long hydrocarbon chain, sometimes you'll see that in a parenthesis with a little 2. On this end hydrocarbon, you see it attached to 2 CH3 groups. So a way to shorten that is to say, oh, I have this pen's driving me crazy. CH3 group, I have 2 of them attached to this carbon, which is attached to 1 hydrogen, which is a CH2 and a CH3. All right, now let's look at what the big structure of this would be. We have a carbon surrounded by 4 hydrogens. I'm not going to put the hydrogens in, I'm just going to put lines. All right, attached to a carbon, and this carbon is attached to another carbon with 3 hydrogens around it. There's a hydrogen coming down, that's this hydrogen right here. And then we have this carbon with 2 hydrogens and this carbon with 3 hydrogens. So this is a full structure. This is a condensed structure. This is even a further condensed structure. All right, so here's a problem. It says convert each compound into a condensed structure. I'd like you to pause it and give it a shot. All right, I'm hoping that you paused it and gave it a shot. if we look at the solution here, here we have 1, 2, 3, 4, 5 total carbons. And here we have CH3, CH, CH2, CH, CH3. So here we have CH3, CH, CH2, CH, CH3. Now on this carbon we do have a CH3 group, and on this carbon we have a CH3 group, which can be seen here. This further simplified, that's kind of crazy. Very rarely will you actually see this. This is more typical. When we look at this structure, we have a CH3, which is right here, CH2 right here, CH2 right here. Next in line is an O, and then a CH2. Here's our O, here's our CH2, and at the end a Cl. And they did further simplify it by sticking these two in a parentheses. I don't think it shortens it up that much, but that could be one way that you see it. All right, now if we draw a skeletal structure, with a skeletal structure we assume there is a carbon atom at the junction of any two lines. Okay, we have to assume there are enough hydrogens around it to give it 4 bonds. And if there are anything other than hydrogens attached, we have to draw them. Now this is kind of wordy. Let's make some sense of this. All right, this is a structural diagram for cyclohexane. How many carbons do you see? 1, 2, 3, 4, 5, 6. The prefix in organic chemistry, meaning 6, is hex. This is a cyclostructure. A shortened way that we can draw this is to just draw this structure right here. So wherever there's a bend, that is a carbon atom. Now we have to assume that each carbon atom is attached to 4 things. One of these things is here, and one of these things is here. If I'm looking at this carbon, that means we have to assume that there are 2 hydrogens. All right, so each carbon is involved with 4 bonds, but we don't put them there. They are just assumed. So being able to take a structure like this and remember what is existing at each of these bends, those are carbon atoms, and knowing that each carbon atom is bonded to 4 things. So we assume that there are 2 hydrogens there. In this case, since we have an oxygen attached, we have to include it. This is this hydrogen is attached to the oxygen, so we would draw it. But we leave all of these hydrogens off. We just assume that they're there. If you notice here, this is an OH group. This is an alcohol. It ends in OL. It's a cyclostructure. There are 5 carbons. 5, the prefix for 5 is pent. This is a cyclo, 1, 2, 3, 4, 5, pent. And since it's an alcohol, enol, cyclopentanol. Okay, we just went through several basic fundamental concepts for an introduction to organic chemistry, and I just want to summarize the major concepts that were discussed in this video. So we talked in general about organic chemistry being all around us. It is fundamentally a study of compounds containing carbon. They can be synthetic or natural. And we talked about a couple of examples. I did introduce some of the terminology and the prefixes that are used. So meth is a prefix that means 1, eth is a prefix that means 2. And we went through some examples of organic compounds, and I commented on how there are regions of different organic compounds that will fit in with certain groups. We talked about ways that we could represent organic compounds and how atoms do connect together in terms of bonding and how we can represent those structures. We also talked about organic compounds being composed of chains and rings, and also that different regions or different types of elements will bond in different ways. So hydrogen has one bond, carbon has four bonds, nitrogen will bond to three things, oxygen typically bonds to two things, and then your halogens, fluorine, chlorine, bromine, and iodine typically bond to one thing. Then we talked about some of your basic structures and shapes. This is called molecular geometry, and when two atoms are in a line, it's called a linear structure. The bond angle is 180 degrees. This is 120 degrees. That it's called trigonal planar. When you have four atoms attached, it is called a tetrahedron or a tetrahedral shape. And when you have three things attached with a lone pair, it's called a trigonal pyramid. When you have two things attached with two lone pairs, it is called bent. And there was a summary. And we talked about how to take a structural formula and turn it into a condensed structure, and then a condensed structure, which is not one of my favorite things, but sometimes you see it. And we finished by talking about skeletal structures in which the lines, wherever there's a bend, represents carbon atoms. And there were these two examples. So that was an introduction to to organic chemistry. I'm going to create a follow-up video, and I'm going to call this part 2, in which I specifically talk about something called functional groups. So that is going to be the end of this video, and I will follow up with my functional groups video, which I most likely will assign you to watch that after watching this. I hope you have a great day.